Alright, starting from this chapter, we are slowly delving into calculus. But to study calculus, we need to know various properties of real numbers more deeply. And also, to know the properties of real numbers, we need to define various notions of regarding sequences of real numbers. So, let's start. One of the most important properties of real numbers is their continuity. And for that, we need many definitions. Okay, so first start from the definition of upper bound and lower bound. Okay, upper and lower bounds. Okay, so suppose S is a subset of real numbers and alpha is a real number. Okay, so this S is any set of real numbers. Okay, and first, if for all x in S, so for any element in S, then if for all element of S, x is less than or equal to alpha. So this alpha is a given value of a real number. Okay, then we say alpha is an upper bound of S. Okay, so this means alpha is greater than or equal to any elements of S. So in this case, alpha is an upper bound of S. And second, if for all elements of S, x is greater than or equal to alpha, then alpha is a lower bound of S. So this means alpha is less than or equal to any of the elements of S. So this is the definition of lower bound. Here are some examples. Okay, examples. Let's say A is a set of real numbers such that x is less than or equal to 1. Okay, then 2 is an upper bound, and 1.5 is an upper bound, and 1 is an upper bound. So they are all upper bounds of A. Okay, so in fact, let's say this is the number line. So this set A, let's say this point is 1. This set A is defined as all real numbers that is less than or equal to 1. So this is A. Okay, so this is A. So any numbers here are upper bounds of A. Okay, and next example, another example, let's say B is a set of real numbers that are greater than square root of 2. Then let's visualize this. So let's say this is square root of 2 and x is greater than square root of 2. So here, this is the set B. So this does not include square root of 2. Okay, and any number less than or equal to square root of 2. So anything here, they are lower bounds of B. including square root of 2 itself. Okay? And consider a similar set. Let's say B prime, or maybe prime is confusing, so let's call it C. So X is a set of rational numbers greater than or greater than square root of 2. So rather than the set of real numbers, it's a set of rational numbers. So again, so it's almost the same as this, but this set C includes only rational numbers in this region. Okay, so any number less than or equal to square root of 2 is a lower bound of C. And of course, there are no upper bounds for C. And now, the next lemma should be quite trivial. Okay, lemma. Let's say S is a subset of real numbers, and alpha, let's call it A. A is a real number. Okay. First, A is not an upper bound. Of S if and only if there is an X in S such that X is greater than A. I think this is trivial, right? If there is some element of S greater than A cannot be the upper bound. A cannot be an upper bound of S. It's trivial. And vice versa. Okay, so it's if and only if. So if you assume A is not an upper bound of S, then there is some X in S such that X is greater than A. And if there is some X in S that is greater than A, then A is not an upper bound by definition, right? So it's trivial. And similarly, A is not a lower bound of S if and only if there exists some X in S such that X is less than A. So it's very similar argument and should be trivial. Okay, so let's move on. Another definition that is bounded above or below. Okay. Above or below. Okay, so again, let S be a subset of real numbers, and if S has an upper bound, then S is bounded above. We say S is bounded above. Okay, so let's say this is 1 and 2. If S has a lower bound, we say S is bounded below. Okay, and if S is bounded above and below, then we say S is bounded. Okay, if S is bounded above and below, then we say S is simply bounded. Okay. the next lemma again should be quite trivial. Okay, so here's another lemma. Let S be a subset of real numbers, and we define the following subsets. So U of S is a subset of real numbers such that for all x in S, x is less than or equal to A. So in other words, this set is the set of all upper bounds of S, right? So any element of this set U of S is greater than or equal to any of the elements of S. So each of A's here is an upper bound of S. And similarly, we define L of S as this. For all x in S, x is greater than or equal to A. So this is the set of all lower bounds of S. Okay, then the following holds. S is bounded above if and only if this U of S is not empty. And I think this is trivial, but you should think about it. And second, S is bounded below if and only if L of S is non-empty. Okay, it should be trivial. Okay, now let's define some more things. We define many things here. It's like learning new vocabulary. Okay, so there are many concepts regarding real numbers, so you should be familiar with all these things. So here's the thing. Definition: supremum and infimum. Okay, so again, S is a subset of real numbers. And let's first, if S is bounded above, and the least upper bound, if exists, is called the supremum of S. Okay, so supremum, we write. I think we don't use this capital letter. So sup S is defined as the least upper bound of S. Of course, an upper bound must exist in this case. Okay, if it doesn't exist, we cannot define supremum. Okay, so supremum of S. And second, infimum of S. We write inf S. So this is the greatest lower bound of S. Of course, in this case, a lower bound must exist. Okay, otherwise we cannot define infimum. Okay, so this is infimum of S. Okay, and we should note that it may be the case that supremum of S may belong to S. Now this is a real number. Okay, it's one value of a real number, And so this real number may be an element of S itself, or it may be otherwise. It can be also the case that the supremum may not be an element of S. So either is possible, depending on the definition of S. Okay, and the same is true for infimum. It may be an element of S or may not be an element of S. Let's see a few examples. Okay. Again, let's say A is a set that of real numbers that is less than or equal to 1 and x. Okay. Then we have, okay, let's visualize this on the number line. So 1. So this set A is all these numbers less than or equal to 1, okay, including 1. So there are a bunch of infinitely many upper bounds of A, but the least of which is 1. So that is this. Okay, 1 is the least value or among all the possible upper bounds of A. So therefore, the supremum of A is 1. Okay? And next example, B, is a set of rational numbers which is greater than or equal to square root of 2. And x is a rational number. Okay? Then let's see. So if this is square root of 2, set B, set B is somewhere here. But it includes only rational numbers, okay? So this square root of 2 itself is not included. Nevertheless, the infimum, so there are infinitely many lower bounds of this set B, but the greatest of which must be square root of 2. Okay? So square root of 2 is less than or equal to any of the elements of B, but it is the greatest value among all the lower bounds of B. So infimum of B in this case is square root of 2. Okay, so it's the greatest lower bound is infimum, and the least upper bound is the supremum. As a next example, consider a closed interval. Let's say A and B. This is a set of real numbers, all real numbers between A and B, including A and B. Okay, so that's important. Then, in this case, the supremum of this interval, between A and B is equal to B. And the infimum of this interval, this closed interval, is A. Okay. In this case, B is obviously the maximum value of of all the elements of this interval, and A is the minimum of all the elements of this interval. So more generally, we can say that if, so let's say S is a subset of real numbers. If S has the maximum, so it has a maximum element, then let's call it B. Okay, maximum element B, then B is the supremum. And if S has the minimum, let's call it A, then A is the infimum of S. So to prove this, just apply the definition of supremum and infimum. If the maximum value is B, then it is obviously greater than or equal to any of the elements of supremum of S. Upper bounds of S. So, sorry, it is the it is greater than or equal to any of the elements of S, and also it is the minimum element of the least element of any upper bounds of S. So, it should be the supremum, and similar for infimum and minimum value. Okay. Next, consider an open interval. So all real numbers between a and b, not including a or b. Okay, we exclude both a and b. Then what is the supremum and infimum of this open interval? Okay, supremum of this open interval between a and b is actually b, right? Because this b is greater than or equal to any of the elements of this interval. Okay, so this b is an upper bound. And among all upper bounds of this interval, this b is the minimum value, it's the least value. Okay, therefore this is the supremum. And infimum of a is interval a between a and b is a. Okay, in this case, this is not, these supremum and infimum are not elements of this subset of real numbers, right? Nevertheless, they are the supremum and the infimum. So as you can see, supremum is somewhat similar to the maximum of a set, and infimum is somehow similar to the minimum of a set, but they are not exactly the same. But we could say that supremum and infimum are generalization of maximum and minimum, respectively. And that's because we can always define supremum and infimum, not quite always, but we can define supremum and infimum even if there are no maximum or minimum in a subset of real numbers. Now let us redefine supremum and infimum based on these examples. So let's redefine. So this is the second definition of supremum and infimum. Sup and inf. So first, and of course S is a subset of real numbers. And so first A is it's a real number is the supremum of S. As if the following two conditions are met. If first condition A, for all elements of S, x is less than or equal to a. So that means this a is an upper bound of S, and b for all if a prime is less than a, then there exists some x in S such that let's say such that x is greater than a prime. So this means if we take any real number that is less than a, okay, so any real number a prime that is less than even slightly, very slightly less than a, then there is some elements, some element of S that is greater than a prime. So this means this a prime cannot be an upper bound of S. So this means this A is not just an upper bound, but it is the least upper bound of S. Okay. And similarly, we can define infimum of R as like this. If A is a real number, then it is the infimum of S if, again, the following two conditions are met. So that is, for all elements of S, X is greater than or equal to A. So this means A is a lower bound of S. Okay? And second, B. If A prime is greater than A, then there is some element X of S that is less than A prime. Okay, so this means if A prime is greater than A, even slightly, very slightly greater than A, this A prime cannot be a lower bound of S. So this means, in other words, this means A is the greatest lower bound of S. So the infimum is defined by these two conditions. It is a lower bound and it is the greatest lower bound. Okay. Now let us prove a little lemma. That is, let's say S and T are subsets of real numbers such that T is a subset of S. Okay. So suppose this. So this is a given condition. Then we have supremum of S is greater than or equal to supremum of T. And second, infimum of S is less than or equal to infimum of T. So let's prove this. Before proving, let me explain what this means by a simple example. Okay, so suppose, for example, in the simplest case, S is an interval. Okay, let's say S is an interval like this. So this is S. And T is a subset of S. So that means T is included in S. So this is T. Okay, so this colored part is T. So the supremum of S is somewhere here. Okay, and the supremum of T is somewhere here. So the supremum of S is greater than or equal to supremum of T, right? And similar for infimum. So infimum of S is somewhere here, and infimum of T is somewhere here. So the infimum of S is less than or equal to infimum of T, right? So, but of course, in general, S may not be just a single interval. Okay, it can contain multiple intervals. It's just a subset of real numbers. So, other than that, we don't have any additional conditions that specifies S and T. So, for example, S can be more complicated, like some points, some intervals here and there. The union of all these can be S, for example. So even in those cases, the supremum of S is always greater than or equal to the supremum of T, as long as T is a subset of S. Okay, so let's prove this. Okay, so suppose A is an element of upper bounds of S. So this is upper bounds, set of upper bounds. Okay. Okay, so that means for all x that is an element of S, we have x is less than or equal to a. Okay, so suppose a is an upper bound of S, then we have this. Okay, but since T is a subset of S, this means for all elements of T, we also have x less than or equal to a. Right? Because all elements of T is also all elements of S. That's the definition of subset. Okay. So this means therefore, this means if A is an upper bound of S, then it is automatically an upper bound of T. Right? So that means, therefore, the minimum of this should be greater than or equal to the minimum of this. Okay. So maybe this is hard to grasp at first. So if A is an element of upper bounds of S, then it is automatically an element of upper bounds of T. So this means, let's see. So let's say this is the set of all upper bounds of S. So then A is an element of upper bounds of T. So that means this subset. Okay, so this subset includes this subset. So the set of upper bounds of T is greater than US. Okay. So the minimum value of U of S is greater than the minimum value of, sorry, this is not U of S, but U of T. Okay. So therefore, the supremum of S, this one, should be greater than the supremum of T, so which is this one. Okay, and we can prove the second part similarly. So second part, okay, maybe I should write here. So U of S is a subset of U of T. I mean, this is the this is the definition of subset. So every element of U of S is an element of U of T. So that means this is a subset of this. And similarly, we can prove that the set of lower bounds of S is a subset of the set of all lower bounds of T by the similar argument. So from this, we can tell that infimum of S is less than or equal to infimum of T. And done. Now we turn our attention to the continuity of real numbers. So first consider this set. So real numbers minus rational numbers. So this is the set of irrational numbers. Okay, so this means if you consider the set of on the number line, if you consider the set of rational numbers, so there are many spaces between any two rational numbers. It's the set of rational numbers is filled with a lot of irrational numbers in between, right? So what about the set of irrational numbers? Is it interspersed with something else? So if you consider the set of real numbers, are there anything that is more dense than real numbers, so that real number is kind of interspersed with something else? It turns out that is not the case. So, so real numbers fills all the spaces on this number line. So there are no extra space other than real numbers on a real number line. Okay, so that is the continuity of real numbers in a nutshell. But we would like to define this concept more precisely later. Here's a simple example that illuminates the continuity of the real numbers. Consider this set. S is a subset of real numbers that is such that x squared is less than 2. Okay. Of course, this is a subset of real numbers, right? And what's the supremum of this set? So let's consider this one. So x squared, okay, so x squared is less than 2. So that means x is between negative square root of 2 and square root of 2. So if this is 0, this is negative square root of 2, and this is positive square root of 2, then this subset represents something like this open interval. Okay. Now, what's the supremum? This is square root of 2, and infimum is negative square root of 2. And of course, these numbers are also elements of real numbers. Okay. But if we consider, so let's say a subset of rational numbers, so x squared is less than 2 and x are all rational numbers. So this is a subset of rational numbers. Okay. In this case, supremum is of course square root of 2, but that is not a rational number. And also infimum, negative square root of 2, is irrational, so that doesn't belong to this set, the set of rational numbers. So the very existence of supremum and infimum within real numbers, so this eliminates the continuity of real numbers. Okay, so based on this, we introduce the following axiom. So here's the axiom. Let S be any subset of real numbers. Okay, first, if S is bounded above, then supremum of S is a real number. Okay, and 2, if S is bounded, S is bounded below, then infimum of S is a real number. Okay, we take these statements as truth. Okay, so this is an axiom. Okay, we accept this as an axiom of real numbers. So we call this continuity axiom. Okay, so this somehow expresses the fact that real numbers is continuous. Now, based on this axiom, we can actually prove Archimedes' principle as a theorem. Remember? In the first lecture, I introduced Archimedes' principle as an axiom, so there was no proof of it. But if we accept the axiom of continuity of real numbers, then actually Archimedes' principle can be derived from it. So what was it? So let A be any positive real number. A positive real number. And B is any real number. It can be negative. Any real number. Okay, uh, then there exists a natural number. Then there exists a natural number n such that an is greater than b. So this was Archimedes' principle. Now, based on this axiom of continuity, we can prove this. Okay, we prove this by contradiction. Okay, so that means let us negate this proposition. So the negation of this is that for all, so let's negate this. There exists some natural number such that an is greater than b. Okay, so if you negate this, that is for all natural numbers, we negate inside this. Okay, so that is if we negate inside this, this becomes this becomes an less than or equal to b. Okay, so that means for all natural numbers, an is less than or equal to b. Okay, so a is a positive real number and b is any real number. Suppose for all natural numbers we have an is less than or equal to b. Okay, so this means, so suppose it's this. Okay, then this means n is less than or equal to b over a. Remember, a is a positive real number, so it's not 0, so we can divide by it. So this means, we are saying all natural numbers here. So this means the set of natural number is bounded above. So therefore, this set of natural number is bounded above. Okay, so according to the continuity axiom, so by the continuity axiom, So there is a supremum, right? The supremum of this set exists. Okay. So the supremum of natural numbers do exist. Exists. Okay. So let S be the supremum. Okay. So S minus 1 is of course less than S, so that cannot be a supremum. The supremum of so that cannot be an upper bound of n. So there is not the supremum. Okay, so if it's not a supremum of n, that means some natural number is greater than s minus 1, right? So therefore there exists some natural number, let's call it m, such that s minus 1 is less than m. Okay. So, but this means s is less than m plus 1. Okay. However, m plus 1 is a natural number because m is a natural number, so m plus 1 is a natural number. Natural number. Okay, is that good? But this natural number is greater than the supremum of the set of natural numbers, which is is a natural number greater than the supremum. Than S. This is a contradiction. So this contradiction came from the assumption that the set of natural number is bounded above. So which came from the assumption that that for all natural numbers this is true. So therefore this must be true. This assumption, the negation of this assumption resulted in a contradiction, so the original assumption must be true. Therefore we are done with this proof. And here is a very trivial corollary. So for any positive real numbers and for any real numbers, any positive real number A and any real number B, there exists a natural number such that A is greater than B over n. This is just the same as the previous theorem, Archimedes Principle, but we just divided both sides by n. That's it. But this form is handy in many cases because this says however big this b is, this b can be negative. In that case, this is trivial. Even if b is positive and very large, larger than a, if we take big enough natural number, then b over n is always it can be always less than a. Okay, let's see one example of this corollary. So that is, let's say we have a set that is 1 over n, where n is any natural number. So if this is the set A, then infimum of this set is 0. So let's prove this. Okay. First of all, for any natural number n, we know that 1 over n is greater than 0. So that's trivial. So that means 0 is a lower bound of A. Okay, and let A be any positive real number. Okay, any positive real. Okay, and by the previous corollary, we know that there exists a natural number such that A is greater than 1 over n. Okay, we can choose such natural number. Okay, so this means no positive real number is a lower bound of this set A. Okay, because any positive number can be greater than some 1 over n for 1 over n for some n, right? So this any A positive real number cannot be a lower bound of this set A. So that is all non-positive real numbers are lower bounds of A, and so the greatest of all non-positive real numbers is 0. So therefore, inf A, that is the greatest lower bound of A, must be 0. And here's another example. Let A and B be some given real numbers. And if for all positive real number epsilon, we have A minus B less than epsilon, then A is equal to B. Okay, so let's prove this. We prove this by contradiction. Okay, so suppose A is not B, then there should be contradiction. Okay, so this means A minus B, its modulus, is a positive real number. So this must be positive real number. So we can find some natural number n such that A minus B modulus is greater than 1 over n. Okay, but this 1 over n is also a positive real number. Okay, so this contradicts this statement, right? So it says for any positive real number, A minus B modulus must be less than epsilon, but it is greater than 1 over n, which is a positive real number. So it's a contradiction. Therefore, A must be equal to B. Alright, we have already proved in the first lecture that the set of rational numbers is dense. But let us prove that again. It's basically the same proof, but just for a review, let's do it again. So here's the theorem. Non-empty empty open interval contains at least one rational number. Okay, so if we have an open interval, however small it is, there is always at least one rational number. Okay, so that's what it says. And we proved this already, but let's do it again. So here's the proof. We consider an open interval from A to B. Okay, and of course A is less than B. And if A is less than 0 and B is greater than 0, then 0 is a rational number that is within this interval. And 0 is a rational number. So this is the statement is true. Okay, and then if both are negative, A is less than B and B is less than 0, then we can then consider the interval negative B from negative B to negative A. Okay, so that is they are both positive. So if this interval contains a rational number, then this interval also contains a rational number, which is the negative of that rational number within this interval. So after all, we need to prove that the case of both positive A and B. So it is sufficient if we prove for this case. Okay, so by Archimedes, to begin with, we can find a natural number such that b minus a n is greater than 1. Right? So by dividing both sides by n, we have, let's see, b minus a greater than 1 over n. So let's see, move a to the right hand side and swap sides. We have a plus 1 over n less than b. Right? And then we apply Archimedes principle again. We can find that let's see, 1 over n times m is greater than a. Okay, so here's another application of so this m is a natural number. Okay, so we apply Archimedes principle to this number and this number, so this and this. Okay, so okay, so let's take the minimum of such m. Okay, so okay, there can be many natural number m so that this inequality holds, but if we take the minimum of such natural number that satisfies this inequality, then that means let's say if m is such the minimum such natural number, so that means if we take m minus 1, then this inequality doesn't hold anymore. So that is m minus 1 over n is less than or equal to a. Right? And from this a is less than m over n. So this a is less than m over n, which is m minus 1 n plus 1 over n. Now we just split m into m minus 1 and 1. Okay, and let's see, from here, from this inequality, that is, wait a minute. Okay, not this one. From here, okay, m minus 1 over n is less than or equal to a. So this is less than or equal to a plus 1 over n. Okay, now we apply this one. Okay, so this one, a plus 1 over n is less than b. Okay, so after all, this means this m over n, which is a rational number, because m is a natural number and n is a natural number. So after all, we have this. And m over n is a rational number. So that's what we are looking for. Okay, so this proof is done. Okay. Now, as a result of the denseness of rational numbers, we have the following corollary. So let alpha be any real number. Okay, then for all positive real number epsilon, there exists a rational number a such that the difference between alpha and a is always less than epsilon. Okay, so this means any real number can be approximated by a rational number to arbitrary precision. Okay, however small this epsilon is, the difference between alpha and a is less than that epsilon. Okay, so let's prove this. Consider the open interval. The open interval. That is alpha minus epsilon and alpha plus epsilon. Okay, and it is important to ensure that this interval is not empty. Okay, since epsilon is 0, so that this interval is not empty. Is not empty. You know, if this is empty, there cannot be any rational number in between, right? So we have to ensure this. We have to make sure this. And so according to the previous theorem, there exists a rational number by the above theorem. Above theorem. There exists a rational number such that A is in this interval, alpha plus epsilon. Okay, but this means, therefore, alpha minus epsilon is greater than A and less than, which is less than alpha plus epsilon. So this means minus epsilon is less than A minus alpha, which is less than epsilon. So this means the absolute value of A minus alpha is less than epsilon. So that's done. So of course this is, we can swap the order within the modulus. So that is done. Let's see a few concrete examples of this fact. So here are examples. So consider square root of 2 and A. So which is less than 0.01. So in this case, epsilon, this is that epsilon, okay, and this is alpha. Now we want to find a rational number A that satisfies this inequality, which is quite easy. For example, okay, so first of all, square root of 2 is something like this. 1 人よ人よに人みごろ. Okay, something like this. So if we take A equal to 1.14, oh sorry, 1.41, then that satisfies this inequality, right? So the difference should be 0.0042 and so on, which is less than 0.01. So that should be fine. But if we take A equal to 1.43, then this is not good. Okay, so this violates this inequality. Okay, second example, pi 3.141592 and so on. This is irrational. Okay, now we want to approximate this by some rational number. Okay, so if we take A equal to 3.14, then this is let's see, this is not sufficiently small to satisfy 0.001. Okay, so this is not good enough, but this is good enough if epsilon is 0.002. Okay, now we study convergence and divergence of sequences and some related notions. So let's consider the sequence such as A1, A2, A3, and so on. Okay, where each AN is a real number. Okay, and of course each N here is a natural number. Okay, and we usually write these sequences as this. So curly brackets and an. Or if you want to specify what this n is, uh, from n from n equal to 1 to infinity, something like that. Okay, so now let's define the limits. Okay, so let an be a sequence. A sequence. Okay, and if an approaches arbitrarily close to a constant value, so this a1, a2, and so on, these values gets closer and closer to certain value that is a real number and certain value alpha, then we call this alpha as the limit of the sequence. So the limit. Okay, this alpha is the limit of the sequence an, and we write lim n going to infinity an is equal to alpha. Or we write an goes to alpha as n goes to infinity. Okay, and we say this sequence an converges to alpha. Okay, and if this sequence does not converge, then converges to any value. Converge to any value. So in that case, we say this sequence diverges. Okay, so the opposite of convergence is divergence. So and if it does not converge to any value, then we say an diverges. Okay. And okay, so this is the definition. So what this means is that as n goes to infinity, so if n gets bigger and bigger, then this difference between an and alpha becomes smaller and smaller. Okay, so this converges to 0 actually. So, but we will make the notion of convergence more precise later. Let's see a few examples of sequences. So first, let's say an is defined by -1 to the power of n over n. Okay, then we have this. So a1 is -1, and a2 is +1/2. A3 is -1/3, and so on. And this converges to 0. So an converges to 0 as n goes to infinity. Okay, so that's one example. And another example, if an is defined to be 3n minus 1, then we have 2, 5, 8, 11, and 14, and so on. So this number only gets bigger and bigger. So this sequence does not converge, so it diverges. In this example, the value of this sequence only gets bigger and bigger, and it diverges. And in this case, we say it diverges to positive infinity. So we write a diverges to positive infinity. Sometimes we write positive sign here as n goes to infinity. Okay. And yet another example. Let's say if an is defined to be negative n squared, then we have -1, -4, -9, and so on. So it diverges to large negative value. In this case, we say the sequence diverges to the negative infinity. So we write limit n to infinity, an is negative infinity. Okay. Obviously, in this case, we cannot omit this negative sign. Okay. And yet another example. Let's say an is -1 to the power of n. So, what's this sequence? When n is 1, that's -1. When n is 2, that's +1. So it oscillates between -1 and +1 indefinitely. It never converges because it doesn't approach any constant, but it's just switches from -1 to +1 and vice versa. So this diverges, and it does not diverge to positive infinity or negative infinity, but it just diverges. Okay, in the sense that it doesn't converge to any constant. So by now, I hope you have some idea about convergence and divergence. But the question now is, what do we really mean by convergence? So to consider this question, consider this particular sequence, an equal to -1 to the power of n over n. So we've seen this example before, but let's write in this way. So here's n, here's an. When n is 1, we have -1. When n is 2, we have +1/2, 0.5. And if we continue this, when n is 10, we have 0.1. And when n is 100, we have 0.01. When n is 1000, we have 0.001. And when n is 10,000, we have 0.0001. Okay, so this means so we've seen that this limit of this sequence is 0. So this means the difference between an and 0 approaches 0 as n goes to infinity. As you can see, so this is -1, 1/2, 0.1, 0.01. So it gets smaller and smaller as n becomes bigger and bigger. Okay, so for example, if n is greater than 100, then the difference between an and 0, an and its limit is less than 0.01. And if n is greater than 1000, then the difference between the sequence value and its limit is less than 0.001. So it gets smaller and smaller. Okay, so if we continue this process, we can generalize like this. So for any small positive number, epsilon, okay, suppose epsilon is 0.0001 and so on, then we can always find, so for any positive real number, we can always find a natural number that is large enough such that if n is greater than small n is greater than so this found capital N, then the difference between an and the limit is less than that epsilon. Okay, so if this epsilon happens to be 0.01, then this large n should be 100 at least. Okay, if this epsilon is 0.001, then this capital N should be at least 1000. So if n is greater than 1000, we can always satisfy this, this inequality. Okay. So based on this observation, we have a more precise definition of convergence. So here's the definition. Convergence. So we write a limit of sequence is alpha if and only if the following is true. So that means for any epsilon, which is a positive real number, there exists a natural number n such that for any natural number, if so this is lowercase n, and if this lowercase n is greater than or equal to the uppercase n, then an minus alpha modulus is less than epsilon. Okay, here we are assuming epsilon is a real number. Okay, so it can be any real number, however small or however large. If it is large, it is very easy to satisfy this inequality. But if epsilon is very small, then it is very hard or maybe impossible to satisfy this equation unless this sequence converges to alpha. Okay. So this is the precise definition of convergence. Let's see an example. So suppose we have a sequence defined by this n over n plus 1. And we can see that this converges to alpha equal to 1. Okay, so if this is true, then for any epsilon, let's say for any epsilon, epsilon equal to 0.01, let's say. Okay, then we can find some number. So that satisfies this. Okay, in this case, alpha is 1 and an is this and epsilon is 0.01. So let's see, for convenience we swap alpha and an. So in this case we have 1 minus n and n plus 1 less than 0.01. And n over n plus 1 is always less than 1, so we can just get rid of this absolute value. And if we solve this inequality, then so this 0.01 is 1 over 100, right? So if we solve this, we find that n should be greater than 99. So if we put capital N equal to 100, then for any natural number that is greater than or equal to 100. We have uh, we have an minus alpha less than 0.01, right? So this procedure can be applied for any value of epsilon, so not just 0.01. So if you want 0.001, just plug in this number and solve the corresponding inequality to find an appropriate value for capital N, and then this should hold always, as long as this alpha is the true value of convergence. Let's see another example. In this case, let us prove that this limit 1 over n converges to 0. So let's pick for any epsilon, positive real number, by Archimedes Principle. By Archimedes, we can find a natural number such that epsilon n is greater than 1, right? So this means, let's see, this means epsilon, oh, wait a minute. This means 1 over n is less than epsilon, right? So if you divide both sides by n, we have this. Okay, so for any n natural number, if this n is greater than or equal to this capital N, then this means 1 over lowercase n is less than or equal to 1 over capital N, which is less than epsilon. Okay, so this means this converges to 0. So because this is of course equal to 1 over n minus 0 absolute value. So for whatever the value of this epsilon is, as long as it's positive, we can always find a natural number that is large enough to satisfy this equation, this inequality. So if our n is greater than this capital N, then this is always less than any epsilon. Okay. Okay. In this definition of convergence, you should know, be careful that you should know that this choice of large N, capital N, depends on the value of epsilon. Okay, also in the previous example, if you set epsilon's value to 0.01, then the value of large N, capital N, is 100. But if you choose another value for epsilon, like 0.001, then the value of this N, capital N, should be different. It should be, I think, larger. So in general, there is no one value of n that fits all values of epsilon. Okay, that's important. For this reason, some people want to write this n as a function of epsilon, something like this, because this does depend on the value of epsilon. Okay, so if you know this, then you should point out what's wrong with this definition of convergence. So wrong definition of convergence. Let's say there exists some natural number such that for all epsilon that is positive real, or for all natural number n if n is greater than capital N, then an minus alpha modulus is less than epsilon. Okay, so this is wrong. Okay, the difference between this and the correct definition is the order of this quantifier and this quantifier. So it's opposite. Okay, so if you write this way, then n cannot depend on epsilon because epsilon appears later. So at the time when this n is defined, there is no reference to epsilons. So this n cannot depend on epsilon. Okay. On the other hand, this epsilon may depend on n, but we say this we use this universal quantifier. So for all epsilon. Okay, so it doesn't really depend on anything. It's just it can be any value. So yeah, this is wrong. Okay, in the next example, we prove that the sequence defined by this, -1 to the power of n, does not converge based on the epsilon n argument. Okay, so to show this doesn't converge, assume it does converge. So we prove by contradiction. Okay, so suppose limit of this an is alpha. Okay, then let epsilon be equal to 1. So there should be there exists a natural number such that if n is greater than n, then an minus alpha is less than 1. Okay, so this indicates so this absolute value is less than 1, so that means this inside this an minus alpha is between -1 and 1. So we don't need this part. So from here, if let's say if n is even, if n is even, then an is equal to 1. So that means 1 minus alpha is less than 1. So this means we put alpha on the right hand side, cancel 1, so alpha is positive. Okay. Then if n is odd, then an is -1. So that means -1 and wait a minute, -1 minus alpha less than 1. So if we multiply both sides, everything by -1, we have 1 greater 1 plus alpha less than 1, and we don't need this part here. So from this part, from the first inequality, we have alpha less than 0. So that means alpha is positive as well as negative, which is obviously a contradiction. Therefore, the sequence and does not converge. It diverges. So it's a contradiction. Next, we give a precise definition of divergence to positive or negative infinity. So we say the sequence an diverges to positive infinity to mean that if and only if for any let's say real number m, there exists a natural number capital N such that for any natural number lowercase n such that if n lowercase n is greater than or equal to uppercase n, then an is greater than m. Okay, so this is the precise definition of divergence to positive infinity. And similarly, we define divergence to negative infinity to mean that for any real number, there exists a natural number n such that for all natural number, if this lowercase n is greater than uppercase n, then an is less than m. Okay, so this is the precise definition of divergence to negative infinity. So what does it mean? Let's consider the divergence to positive infinity. Okay, so it says for any value of a real number, let's pick m. Okay, so we have a sequence which diverges to infinity. Well, in some way. So let's pick any real number m. Okay, so if we take large enough n, so capital N, okay, then if we pick large enough n, then after that all the values of the sequence is greater than this chosen value of m. Okay, so that's greater. So actually n should be somewhere here. So after this point, all the values of the sequence is greater than this value. So that's the meaning of divergence. So if we choose any bigger number m, so in that case we should choose some bigger number of n, right, accordingly. So if we choose from here instead of this, we choose this n, so that after this the values of this sequence are greater than the chosen value of m. So this, we can choose some n always for any value of m. Okay, so that's the meaning of divergence to positive infinity, and similar for negative infinity. All right, this lecture is getting a little long, so let's have a break here. And this will continue to part 2. See you later.